let's say we've got the following. Here we've got just a flat surface, and we've got a little cart or a trailer or a trolley of some sort that is moving on this. It's a frictionless surface, and this trolley is moving at a constant speed equals to, let's say, 2 meters per second in the positive x direction. And somewhere over here we've got a mass. Let's say the trolley has got a mass of 3 kilograms. Here we've got a 2 kilogram mass, and it has just been released, so its initial velocity is 0, and it can fall half a meter before it basically falls onto the trolley. Right, so this is our initial setup. And then at some later time, we've got that the mass has now fallen on the trolley. So we've got this. There's our trolley, 3 kilograms. This is our mass on top of the trolley now, 2 kilograms. And both of these are moving now together, so they both have got the same final velocity, which we do not know. So the question is, firstly, is momentum conserved? And secondly, is calculate the final velocity of the trolley and the mass together. Now let's look at the first question. Is momentum conserved? Right, let's look at the instant right before this mass has, hits the trolley. So this mass, after it has fallen 0.5 meters, so right before it hits the trolley. So we take our before time, that's right before mass lands on trolley, and our after is immediately after the mass landed on our trolley. Okay, so let's look at what is the momentum before. So let's first look at the x components. So the momentum in x is basically, we can say in generally, it's the x component of the momentum of the trolley plus the x component of the momentum of our 2 kilogram mass. Now this is equals to 0 because the mass only moves downward. So it doesn't have momentum along x because its velocity is along y. So it's got no momentum along x. So the total momentum before is equals to the x momentum of the trolley, which is just m times its velocity, which is 3 kilograms. So we can, instead of writing in vectors, we know the velocity will only have an x component anyway, so we can simplify this. So it's 3 kilograms times 2 meters per second, and that's just 6 kilograms meters per second. So the units of linear momentum is just kilograms meters per second. So how much mass is moving how fast? So this is our total momentum before. In vector notation, we can say the total momentum before is just 6 kilograms meters per second in the x direction. Let's look at our momentum after. So, we still have to do the y component as well. So there might be something added over there. So let's look at the y component. Now the trolley is not moving along the y direction, so it's got no velocity along y. The only thing that has got velocity along y will be this mass, which is falling downwards. So we must figure out first how fast it is moving right before it hits the trolley. So this, the total momentum before in y is equals to 2 kilograms times the final velocity, or the velocity of the mass before it hits the trolley. To calculate that, we can use just simply our equations of motion. We know in general that final velocity squared is equals to initial velocity squared plus 2 times acceleration times displacement. Here we start with initial velocity of 0, so this mass, when it was dropped 0.5 meters above the trolley, it had no velocity. So that becomes a 0 minus 2 times 9.8, that's acceleration, minus 0.5. So we find that the final velocity is equals to the square root of 9.8. And if you calculate that, you get that this is just 3.13 meters per second. And it will be downwards. So this means the total momentum right before this mass hits the trolley in the y direction is 2 kgs times 3.13 meters per second, and it will be downwards, and that is just 6.26 kilograms meters per second downwards. So it means we have our total momentum before is equals to the momentum of the trolley, which is in the x direction, plus the momentum of the mass, which is in the negative y direction. So it will be negative 6.26 kilograms meters per second along the y direction. So that's our total momentum before these two things collide. Now let's look at the momentum after. So after the collision, so after the block has landed on the trolley, we've got our trolley over here, we've got the block over there, and both of them are moving in that direction. So now our total momentum is going to be, this now moves as one single object with a combined mass. So we can add the 3 kilograms of the trolley and the 2 kilograms of this mass to a single mass, and it will be moving with some final velocity. So this will be equals to 5 kilograms times whatever the final velocity is, and it will be in the positive x direction. Now if we compare this to the total momentum before, we can immediately see that the momentum after is not equals to the momentum before, because this is owned purely in the x direction. This has got an x and a y component. So already from this, no matter what the magnitudes are, we know that this vector will point in a different direction than that vector, so they cannot be equal. So momentum is not conserved. The question is, why is momentum not conserved in this instance? So we said momentum is conserved for an isolated system. Now, this is actually not an isolated system, because when the mass hits the trolley, so when the mass hits the trolley, there is a normal force from the earth on the trolley that prevents it from moving into the surface. And that force does two things. First of all, it immediately stops this mass dead in its tracks, so it affects the motion of the system. and it comes from an external agent, in this case the surface. Remember, the surface was not part of our system. So this normal force is an external force, therefore momentum not conserved. However, if we look at only the x components, so if we only look at the x components, there's no force in the x direction ever. So there's no external force, or all the external forces have got 0 x components. So whatever our external forces is, its x component is 0. Now this implies that the x component of the total momentum will be conserved. So momentum, the y components, momentum along the y direction is not conserved because our external force acts along the y direction. Along the x direction, we don't have any external force component, so we expect the x momentums, or the x component of the momentum to be conserved. Now we already know what this is. So the momentum before, its x component was just 6 kilograms meters per second, and it was in the positive x direction, so I'm just going to keep this positive. This must now be equals to the total momentum along x after, which we know is that. Also in the positive x direction, so this is 5 kilograms times the final velocity. So our final velocity in the x direction is just 5 divided by 6 meters per second, and you can calculate that as a decimal number if you want, but that is your final answer. Yes, sorry, it is 6 over 5, sorry, because you have to divide 6 by 5 leaves you the final. Right, so that is an example of how you can apply conservation of momentum to solve problems of motion.